G'day, in this video we're going to start to unpack the concept of transformers, which is an application of Faraday's and Lenz's law. In particular, this video focuses on content from dot point 6.3.2 and 3. We're looking at stationary and moving charged particles and their interaction with an electric and magnetic field, essentially focusing on an application of electromagnetic induction, which are defined by Faraday's and Lenz's law, particularly looking at transformers and this concept of an ideal transformer. There's two equations that we will be introducing today, which will help us to not only know how a transformer works, but also begin to apply some quantitative concepts as well. So our key learning intentions. First, we're going to outline the general role of a transformer, then apply Faraday and Lenz's law to explain the basic principles of how ideal transformers work. And then using Faraday and Lenz's law, we're going to be able to get some quantitative relationships that exist for ideal transformers so that we can begin to do some problem solving and calculation with them. So a transformer, essentially what it can do is adjust the voltage and current of an electric circuit. So we see that in a bunch of places. You'll find that transformers are used in terms of the distribution of electricity through our electricity grid, but also transformers exist so that the power that's coming out of the mains can be converted into a certain current and voltage which are compatible with the electronic device which is being powered. So you'll see transformers attached to devices which plug into the mains to make that transformation of electrical energy happen. In particular, the big boxes which are found on like laptop chargers are transformers in and of themselves. They're also built into wall chargers for like a USB charger that you might use for something like a phone. So an ideal transformer. We're going to look at this concept first. When we say that we have a transformer which is ideal, essentially we're making a bunch of assumptions that essentially dictate that the transformer is working at its theoretical maximum efficiency. And with these assumptions, we can start to derive some of the equations, which I will show you in the last part of the video. But for a transformer, essentially, we've got AC current, which is flowing through a primary coil, just like the one that's in this diagram. AC meaning alternating current, meaning that the current will go at this top point from left to right and right to left, and that will alternate over and over and over again. This alternation of current is going to generate a magnetic field, but a magnetic field which changes. So if we got current going through from left to right, it's going to induce a magnetic field which is pointing in the upwards direction. And that magnetic field is able to be carried through a ferromagnetic core, essentially a piece of metal, generally iron, which is able to allow this magnetic field to travel throughout the entire core. What you end up with is like a closed circuit almost of a magnetic field that's able to run around the entire core. So if you're generating a magnetic field on the left-hand side here, and a magnetic field is moving around the core, it's then going to start to interact with the loop, which is on the other side, the secondary coil. So the magnetic flux or the magnetic field is able to get to this secondary core and interact with it. And here we have an induced current in this secondary coil. And this is because there is a change in flux. It's not just enough to have the magnetic field running through the core and past the coil. There needs to be a change in flux, meaning that there is a change in magnetic field. Essentially, if you have an alternating current, there's going to be a change in the current of the primary coil. The change of the current of the primary coil will have an influence on the amount of magnetic field which is being generated here, and thus have an influence on the magnetic flux. That change in magnetic flux, as the magnetic flux changes and passes through the secondary coil, is what induces current. There's a little bit more information about the primary and secondary coils, as well as the transformer core over here. Feel free to read that. And in the diagram, what I want to point out is that on the left-hand side, we have the primary coil that has a voltage VP, a current IP, and also has a certain number of turns in the coil, which is given as NP. And over here on the right-hand side, we have the secondary coil, which has a voltage, a current, IS and VS, and NS representing the number of turns in the coil. As I'm going to show you in our final slide when we look at our quantitative relationships, the idea of the transformer is to have a starting voltage and current, generate a different voltage and current, and the way in which this is achieved is by having different numbers of turns for the primary and secondary coil. This will either increase the voltage and decrease the current, or increase the current and decrease the voltage. Keep in mind too, the direction of current at any given time is determined by Lenz's law, which maybe you can have a look at there to try and figure out why both currents are pointing from left to right in this diagram. It is something that we will discuss in class though. So our quantitative relationships, they're at the bottom of our electricity and magnetism section of our data sheet. We've got Vp on Vs is equal to Np on Ns, as well as Vpip is equal to Vsis. I'm going to show you a derivation for both of them in which I'll apply Faraday's law, as well as our equation for power, which we learnt about in Module 4. What I'm going to do is apply Faraday's law to both the primary coil and the secondary coil. So what I've written here is that for the primary coil, the electromotive force, or Vp, is equal to the number of turns in the primary coil multiplied by the change in flux over the change in time, which will be dictated by the alternating current. Similarly, Vs here, the voltage or electromotive force, which is induced into the secondary coil, is going to be equal to negative of the number of turns in the secondary coil multiplied by the change in flux over the change in time. Underneath, I've done a rewrite of both of those equations and moved the voltages, or the electromotive force, and the number of turns over onto the left-hand side, leaving us with two statements: negative change in flux over change in time. From here, we're going to make an assumption, and that is that the change in flux over the change in time for both coils are going to be the same both for the primary and secondary coil. And this is assumed that essentially the change in flux carried through the core is going to be consistent throughout the core. If that's the case, what we see is that the electromotive force of the primary coil divided by the number of turns is equal to the electromotive force which is induced into the secondary coil divided by its number of turns. We can rewrite this so that one side of the equation includes all the voltages and one side of the equation includes all of the turns. So what we can see here is that there is a really close relationship between the ratio of the voltages in the coils and the number of turns in both of the coils. They work in the same ratio. We'll have a look at applying this concept a little bit further when we get into class. There is, however, one more concept that I want to unpack, and this will show us the relationship between the currents of the primary and the secondary coils. So in an ideal transformer, what we'll assume is that we have 100% efficiency. Essentially, all energy that we have at the start is going to be ending up over at the other side in our secondary coil, or power output is equal to power input. We can also rewrite that using our power equation. We could also say here that the power of the primary coil is equal to Vpip, which is all equal to the power of the secondary coil, which is Vsis. So what that means is, to clean everything up, the product of the voltage and current in the primary coil is equal to the product of the voltage and current in the secondary coil. To do a rearrange, I'm going to put all my voltages on one side. I've got Vp on Vs. The rearrange tells us that that is equal to Is on Ip. So when we look at the two equations that we've got here at the end, we can see that the left-hand side is the same, Vp on Vs. What that means is that our statements which involve N and I are also equal to each other. So there we go. We've got a relationship now between the voltages, currents, as well as the number of turns in our primary and secondary coil. The last thing that I want to share here is, if we unpack our power equation, or our version of the power equation which relates Vp, Ip, and Vs, a conclusion that we can make is that if we increase the voltage in the secondary coil, that's going to lead to a decrease in current in the secondary coil, and vice versa. If we increase current in the secondary coil, that's going to lead to a decrease in voltage in the secondary coil, which is kind of the whole point of a transformer. Depending on the number of turns that we've got when we compare the left-hand side, the primary, and the right-hand side, the secondary, it's going to have an impact on the current and the voltage. It's either going to increase one and decrease the other, or vice versa. And as such, as I said at the beginning of the video, that is the entire role of the transformer, to adjust the voltage and current in an electrical circuit so that the electric current that's moving through is going to be compatible with whatever components are receiving that electrical energy. We'll expand on that concept again a little bit more in class. Thank you very much, everyone. In the next video, we're going to break down a little bit further how we can apply the transformer into a variety of situations and also discuss some limitations for transformers. In actuality, we don't really operate with ideal transformers. We get pretty close, but we are going to talk about some of the limitations of the model or the mathematical models that we have just sort of derived in this video. But until then, have a good one.